11, there will be a bus going for ATM trip. Okay. So if you want to withdraw money, so for the newcomers mostly, after the coffee break, look for Raphael. Okay, we'll be around. We'll be near the entrance, and he will take you guys to withdraw money. So apart from that, so tonight there is a conference dinner. You will receive. Okay, maybe we will shift the talks of the evening by half an hour. But I will send you an email, or someone will send you an email about that later today. Okay, so that's it for now. Yes, but I will tell you. Okay, so that's it. So, okay. Please, you can start.
Okay. So first of all, thanks to the organizers for inviting me, and also for helping me with the many political problems that I had. So I'm very happy to be here. This is my first time in Brazil. I'm happy to be here. If you recognize the picture, no, okay, the pointer doesn't work. If you recognize the picture, you will know that I'm a big fan of Brazil. So I'm quite happy to be here. Also, maybe I should apologize. I think this talk was supposed to come early in the workshop, but I couldn't be here last week. So it's a little funny to hear about this in the middle, but maybe with enough new people here, it's still interesting. Okay, so this is the charge that I got from the organizers about what I should talk about. So how and where is that looking for new physics, and what is the reach? How do we make sure nothing is missed? And then how are results presented and what efforts are made for reinterpretation. So that was very nice because it leads right into the outline, which follows exactly the charge, I think. So there's a brief introduction to Run2. And then, okay, then the first question, actually, it's easy to answer. It's also very difficult to answer because how do we look for new physics? Well, basically, every analysis that Atlas publishes is in some sense a search for new physics. We're always looking for deviations from the standard model. So that's an easy answer. It's a little bit more difficult to summarize in a talk like this. So I rapidly go through a few examples and give some numbers for the prospects or for the reach where they're available. And then there's the question of is everything covered, and then that leads naturally into this question of the Atlas presentation results for reinterpretation. Does this work? Oh, okay. Okay, so let me just give a few caveats at the beginning. So, of course, as usual, for the Atlas results themselves, I only show the official Atlas results. That's normal. Since this is a workshop, I took some liberty, and so I make some remarks, and I just want to say that that's not the position of Atlas. These are just my own opinions. And then I also want to point out, in many cases, that I'm using the Atlas projections to larger integrated luminosity. And just a word of warning, so some caution is needed when looking at these numbers, and especially if you want to compare them to current results that we have already, because many of these projections are a bit old. First of all, they were quite conservative, and also many of the analysis techniques that are included there are either conservative or old, so that they may not reflect the state of the art. And so it may give the impression that when you compare to current results, there's not actually much to gain by going to more integrated luminosity. And that's not the impression that I want to give. I just want to compare them because I think it's sort of useful and interesting. And in particular, in these slides, although I don't say it, I'm sort of suggesting, without any basis, that there are many projections from Atlas, for instance, the 300 inverse femtobarns at 14 TeV. But you may make an ansatz that those projections to 300 inverse femtobarns, given that they're somewhat conservative, they may give us some idea of where we would be at the end of Run2, which is about a 150 inverse femtobarns. So that's kind of my philosophy for showing these numbers, but it needs definitely a huge grain of salt. So one shouldn't take it too seriously. Okay, so this is, you've seen this also yesterday. This is the long-range plan for the LHC. And we are right here, roughly in the middle of run 2. The goal of the run is to collect 150 inverse femtobarns. And so this we also saw yesterday. The LHC performance has been excellent. Peak luminosity this year is reaching 2 × 10⁻34. That also gives the big problem on the plot on the right of the pileup. In particular, the yellow curve, which is the pileup in 2017, which is an average of 37.5. So there's 46.9 inverse femtobarns recorded in 2017, as of a few days ago. And then also on the data already collected, the analyses that I'm going to talk about today are mostly based on roughly 36 inverse femtobarns of data recorded mainly in 2016. So this is already roughly something like a little bit over 80 inverse femtobarns already recorded. All right, we also have excellent performance of the standard model. So this is the usual Atlas summary plot of the standard model covering about 14 orders of magnitude with very good agreement between measurement and prediction. I also put on the right, it's not often shown this way, but a few cross-sections from BSM searches. So just to give you sort of the range where we are in cross-section when you're going out to very extreme phase space. So there's the Gluino going to TT bar and neutralino. This is the cross-section for massless neutrino, and a 1.9 TeV Gluino is around 1 femtobarn, and then KK graviton is around 0.1 femtobarns for 5 TeV. All right, so now let's go through some of the topics. So let's start with the Higgs. So in terms of where we started in run 2, the run 1 legacy. So after the discovery in 2012, the main discovery channels, which are the Diboson channels, gamma gamma and WW and ZZ, in the gluon-gluon fusion channel. So those decay channels are now firmly established. Also, at the end of the run, thanks to a combination with CMS, there's over 5 sigma observation of Higgs to tau tau, and also observation of the VVF production mode. And then also interesting is this starting of an investigation of a 5x5 matrix of production mode versus decay channel, which is sort of summarized in this plot in the middle. Where with the combination, we're starting to get sensitivity to many of those elements in that 5x5 matrix. So one of the important things left open from run 1 was actually there was no direct evidence of coupling of the Higgs to quarks, although of course there's indirect evidence through the loops. So that was an important topic for the start of run 2. And so let's go into that. So the first one I want to talk about is Higgs to BB. And here we have 3 search channels in ZH and WH, going to nu BB or L nu BB or LL BB. There's a kinematic fit in the ZH case, in the LL case, that improves the mass resolution. And generally, one's looking at high boosts or high PT of the vector boson. So it's like many of these analyses is based on a BDT, and which is cross-checked with a separate BDT, which actually looks for the WZ or ZZ production with Z going to BB bar. So you see on the top right the output of the BDT. So this is ordered in terms of signal to background, and you can see maybe on the bottom plot the sort of the evidence for the signal starting to appear at high signal to noise. The bottom plot is a simpler analysis without a BDT, just relying on the dijet mass, and there also you can see this nice excess indicating the signal. So these are the results. So 13 TeV alone is shown on the left. So there's a signal strength combining all the channels of about 1.2 with error of around 0.4. One can also do a combination with the earlier measurements, which have not too much sensitivity, but then that gives the result on the bottom, the signal strength of 0.9, slightly reduced errors. So that was the evidence for Higgs to BB. Now we also have TTH, and so the first channel is TTH production with Higgs to BB. So there's several signal regions. There's a 1 lepton signal region boosted, dilepton signal region. There's actually 3 of them that differ in the B tagging requirements, and then a 1 lepton resolved analysis, which also has 3 signal regions, here requiring 6 or more jets. And then, so there's 3 of them with 6 or more jets, and then 2 signal regions that require 5 jets, exactly. And here again, there's a number of BDTs that are involved. So there's the so-called classification BDT that tries to separate TTH from TT bar background. And this includes a number of things. There's a likelihood discriminant that targets TT bar plus B jets, and then there's also a matrix element method approach, which is used only since it's very CPU intensive. It's implemented only in the most sensitive 1 lepton region. And then also feeding this classification BDT is another BDT that tries to match reconstructed objects to partons and tries to identify the final state objects in terms of partons. And so these are the results. Again, this is the output of the BDT on the left. So again, ordered in terms of improving signal to noise towards the right. So there's really not much. I mean, there's a hint of something. It's a 1.4 sigma observation versus 1.6 sigma expected. And you can see the signal strength on the right. So there are 2 separate signal strengths for the dilepton and the single lepton. So they're allowed to be independent, although the nuisance parameters are kept correlated. So more interesting is the TTH production with Higgs going to multileptons. So this has a number of Higgs decay modes contributing, WW, tau, tau, and ZZ. And there are 7 event categories based on the number of electrons and muons, light leptons on the x-axis, and the number of taus on the y-axis. Again, there's a number of BDTs involved. There's a BDT for non-prompt lepton rejection. There's also other BDTs for each of the categories, tailored to that category for the backgrounds in that category. And in the end, the analysis is based on 8 signal regions, where the 4 lepton region is split into a Z enriched and Z depleted. And so the plot on the bottom is sort of interesting. It shows you the 8 different signal regions, and then the makeup of what the signal regions are sensitive to, which decay modes. So you can see the breakdown. So it's, a large part of it for many of them is from WW, and then later on one gets more sensitivity to tau-tau modes. So again, this is the plot of the BDT output versus signal to noise. And so here one starts to see a clear excess in high signal to noise region. The table shows you the contribution of the different signal regions. So there's overall, the significance is 4.1 sigma versus 2.8 expected, so maybe a little bit lucky, or maybe some new physics. In particular, there's a sort of a 3.4 sigma in this 2 lepton same sign plus hadronic tau case, where there's a little bit more than expected. So then, although this has the most power, one can then combine it with other searches for TTH with the other Higgs decay modes. And so in the end, one ends up with the background-only hypothesis being rejected at 4.2 sigma versus 3.8 sigma expected. So this is evidence for TTH production. Okay, then a little bit about some of the diboson modes, Higgs to gamma gamma and ZZ star to 4 lepton. So here the Higgs to gamma gamma is based on 31 exclusive event categories that's sensitive to different mixtures of the production modes and kinematic regions. Higgs to 4 lepton has 9 categories. The plot on the left is the familiar one of the gamma gamma, the bump, which is starting to appear quite nicely, and then also the 4 lepton peak, which is also becoming very nice now. The plot on the bottom shows the signal strengths from the two modes. There's also a combination of the two, which is described in that conf note, which I'll mention a little bit about in the next slide. So these are this allows gives the sensitivity to the different production modes that's shown on the left, and so it's mainly sensitive to gluon-gluon fusion, but there's a bit of sensitivity also to VBF. The plot on the right shows this in a different way. It's just the cross-section times branching ratio normalized to the standard model. A new development is that these higher sensitivity analyses are now moving towards differential measurements and measurements of these simplified template cross-sections, which are basically they're cross-sections in fiducial regions that are sensitive to different production modes in specific regions of phase space. So you can see the plot on the bottom that has the definitions of many of these and the results of the measurement compared to the standard model. And generally speaking, there's reasonable agreement across all the regions. So this is sort of a bit of a summary. So these are the Higgs signal strengths. So the 13 TeV results I show on the left that I've just shown, and with the errors. And then on the right is the again fairly old but projection to 300 and 3000 inverse femtobarns. So the 300, which is maybe more interesting here for the sort of the run 2 reach maybe, is shown in the green. And so it's roughly, so there's a little bit more to gain. There's where, so for instance, especially BB bar, 35% could maybe come down to, I don't know, looks like maybe 25 or so. So that's something to look forward to for the end of run 2 and maybe run 3. All right, so then related to Higgs production is VBS and also tribosons. So here in run 1, there was the evidence for the same sign electroweak production of WW in this VBS signal region, so that's shown on the right. So this is looking at high dijet invariant mass and also large rapidity separation. And so you can see in the light blue the evidence for the signal. So it was roughly 3.6 sigma observed versus 2.3 sigma expected. And then one can improve the sensitivities to some of these parameters, operators, by furthermore requiring the invariant mass, the transverse mass of the WW system to be over 400 GeV. That's shown on the bottom, and some indication of what in the white what it would look like for this particular selection of these parameters. And then the plot on the bottom left is the exclusion limits for the alpha 4 and alpha 5. So there are actually no results yet with 13 TeV data on vector boson scattering. I just show here a plot on the left. This is for 3000 inverse femtobarns, but you can sort of scale it down to give an idea of 300 inverse femtobarns. So this is, one could expect maybe order few hundreds of events. And then the plot on the right shows the prospects at 300 and 3000 inverse femtobarns for one of these, I think, dimension 8 operators. There's also a whole catalog of other operators and with the sensitivities for where one might be with a discovery, depending on what these would be the limits on those parameters if those were the sources of deviation from standard model in the future. A little bit about tribosons. So tribosons, they were starting to be observed in run 1. For instance, there's a clear signal for Z gamma gamma. So this is from run 1, 6.3 sigma effect. The 14 TeV prospects have a slightly different selection. So the selection on the top is a fairly inclusive selection. This plot on the bottom is a much more restricted selection designed to be more sensitive to anomalous couplings. And so this is again the plot for 3,000 inverse femtobarns, but there's a table that gives some indication of the reach for 300 inverse femtobarns in tribosons. Generally, they're less sensitive than vector boson scattering, but they're interesting also as a cross-check. So this was the summary at the moment of where things are in vector boson scattering, vector boson fusion, and also triboson. And so the color coding, most of these, which are sort of orangish red, are the 8 TeV results, and the purple ones, which are the 13 TeV, there's a few. The top one actually comes from the Higgs combination that I talked about earlier. So there's still many to come, and so that's something to look forward to in run 2, the rest of run 2. All right, so then a little bit about dibosons, diboson resonances. So this was an area with a lot of excitement in early run 2. There was the famous 750 GeV bump in gamma-gamma. There was also an excess in WW and WZ resonances, although maybe less exciting. It was a 2.5 sigma local significance at around 1.6 TeV. So what's shown here is the run 2 resonance search for WW and WZ in the L nu QQ final state. One new feature in the new analysis is that there's a separation between VBF and gluon-gluoson or Drell-Yan categories. They're treated separately. So here I just show a couple of plots from the VBF category of events, assuming tailored to slightly different production or signal categories, W prime and Z prime. So yeah, I mean, there's a bit of a shoulder there, and so yeah, that's something to keep an eye on. The largest excess is 2.7 sigma, but that's local, so in a global sense, it's still somewhat interesting, but maybe nothing to get too excited about. There's also searches in LLQQ and nu QQ final states. So those are shown here. So on the left is in a gluon-gluon fusion channel in LLQQ and nu QQ. Yeah, no sign of any new physics, and then also on the right in the Drell-Yan channel, Drell-Yan analysis. There's also the all-hadronic final state. So this looks at all combinations. It can't really distinguish between W and Z. And so here again, there's really no sign of any big deviation. So there's WW plus WZ on the left and WW plus ZZ on the right. And yeah, they all look fairly unexciting at the moment. And then the gamma-gamma search, so this is in the high mass region. There were 2 selections, if you remember, from the beginning of run 2, a spin 0 selection and a spin 2 selection. So in the 750 GeV region, there's really, yeah, nothing interesting anymore. And in general, everything looks quite consistent with expectations, with the background only fit. All right, then a little bit more about resonances in a slightly different vein, the vector-like top quarks. So these appear in sort of the alternative to SUSY if you're interested in naturalness and solving the naturalness problem. So the little Higgs or composite Higgs models, which is the main alternative. These vector-like top quarks appear, vector-like quarks appear. And so these searches are geared towards the vector-like top quark, which mainly the case the 3 modes, Z top, Higgs top, or WB. So all 3 of these decay modes are searched for simultaneously, although one assumes there's a pair production of TT. So these plots are a little bit maybe, they contain a lot of information, but if you look at the plot on the left, it's as a function of the branching ratio of this vector-like quark to WB versus on the y-axis the Higgs top branching ratio. And then the contours are showing the mass limit on based on the ZT channel observation, the mass limit on vector-like quarks as a function of these two branching ratios. And so you can see, that it starts at around 800 GeV for high branching ratios to the other modes, and then one gets stronger and stronger as the ZT branching ratio gets more prominent. The plot on the right is the analysis in the WB, looking for the WB final state in the 1 lepton channel with a similar interpretation, again as a function of the two branching ratios. And so this is a sort of nice plot, the nice summary plot, which is again in this plane of the two branching ratios, and then showing how the various dedicated searches are covering this plane as a function of the mass of the vector-like quark. So for low masses, when you combine the different analyses, basically the plane is totally covered, it's excluded. And then as you go to higher masses, there are regions in white that start to open up that are still not excluded yet. All right, SUSY. So let's start with Gluino pair production. So most channels looking for Gluino pair production have finished with the 2015 and 2016 data. And this is the summary plot on the right, which shows a sampling of many of the Gluino decay modes that are searched for. And so in some cases, you can see that the Gluino mass limits are approaching or have exceeded maybe 2 TeV in some cases for massless neutralino. This is an example of the limit in the jets plus missing ET, so no lepton inclusive channel, just highlighting again the exclusion out to 2 TeV. And also showing the improvement over the initial analysis, which was based on 2015 data only. And so the prospects, this comes from, again, somewhat old analysis. This one can see in the same channel, in the 0 lepton channel, where one might be at 300 inverse femtobarns and 3,000 inverse femtobarns. And so the curve of interest, for instance, of 300 inverse femtobarns, this is the 5 sigma discovery line. And then this is the dotted one is the 95% exclusion for 300 inverse femtobarns. So that reaches roughly 2.3 TeV for this Gluino to light. So I don't know if this helps, but you can overlay them and sort of squeeze them together. So this is sort of where we are. And actually, so 5 sigma discovery is not possible, even with 300 inverse femtobarns. And then this is where one might go with 300 inverse femtobarns. Or maybe by the end of run 2, one could reach that high. All right, what about top 3rd generation squarks? So this is the summary plot from the Atlas SUSY summary page. It needs a bit of an update. The results haven't changed, but many of the analyses have already been submitted for publication, so they're no longer these conf notes. In particular, in this round of analysis, there was special attention paid to developing signal regions that are sensitive to the compressed 2-body stop decays, which is around here, and then the 3-body and the 4-body stop decays. But in the 2-body case, in the high mass range, the limits are approaching 1 TeV, which was sort of a milestone based on these naturalness arguments. Although this does assume 100% branching ratio to this particular decay mode. There are, I guess I didn't put it here, but there are also studies of the reach depending on the branching ratio, and they're of course weaker, but they're also fairly significant. And so you may want to have a look in the paper for those. The prospects are shown here. So here, the plot on the right, this is actually a combination of the 0 and 1 lepton channels, which gives a little bit of a boost to the sensitivity. So in the high mass region, the 95% exclusion would go to about 1.2 TeV with 300 inverse femtobarns. And then the plot on the left, on the bottom, is the prospects now in the compressed region for the two-body decays. So this is actually in the 2 lepton channel analysis. And if you look at, you would look here at sort of 5% P0 for the 95% exclusion. And so that's reaching around 600 GeV for 300 inverse femtobarn. And so that's in the 2 lepton channel, which may actually not be the most sensitive channel. This is something that's still under investigation. But if you see here already, some of the like the 0 lepton is approaching sort of 550-ish already with 36 inverse femtobarns of data. Right. Now, one kind of surprise for us this time was there was a difficult scenario that turned out to be, we had less sensitivity than we might have thought. So this is a PMSM model that's inspired by this well-tempered neutralino scenario for the electroweak sector. In this model, only bottom and top squark production are considered. And you can see the exclusion plots in the stop LSP plane and for stop left in red and stop right in blue. So you can see, for instance, in the top that the stop right limits are significantly worse. And in fact, in the 1 lepton analysis on the bottom, the sensitivity is fairly shallow. So although there's an expected exclusion based on this dotted line, there's a slight excess in the data, nothing significant, but that's enough to the observed exclusion off the plot. So there's actually no exclusion at all of this particular model in that channel. So this is maybe something that we plan to revisit and maybe re-optimize for these types of scenarios. These tend to be scenarios with long decay chains, which is, I guess, has been known for a long time that the analyses are not as sensitive to, since they're mostly optimized for two-body decays. In the electroweak sector, there's so far not too much. Most of the results are still coming. This is the summary plot. As of now, there's really only one 13 TeV result, which is this one here in brown. So looking for chargino-neutralino pair production with the decay to the WZ final state. So that's reaching something like 570 GeV at the high end for low mass neutralino 1. You can also see, for instance, that the limits, these are still from run 1, are still quite weak for chargino neutralino pair production where the neutralino 2 decays via Higgs. So then what would be the prospect? So with 300 inverse femtobarns, then the 95% exclusion in the WZ mode could go up to about 840 GeV. So that's fairly significant improvement compared to what's achieved so far in run 2. And then for the WH mode also, this is with the WH with Higgs to BB. With 300 inverse femtobarns, the exclusion 95% would extend to about 900 GeV. So that's something to keep an eye on for run 2. Okay, so let me make some remarks before going into the final part of the talk. So some remarks about LHC Chapter II. So I only covered a small fraction of the results here. There are many other analyses that are complete with the data taken in 2015 and 16. What can be expected to be coming out fairly soon? So there will be more results on electroweak SUSY, on long-lived particle searches, various other exotic signatures that are searched for, possibly some results on rare decay in B and taus. There are BSM Higgs searches. There's also BSM di-Higgs production that we heard about yesterday. Also results on exotic Higgs decays should be coming out. And probably I've forgotten some things here. And then also I think what one can keep an eye on are the studies of the interplay between the Higgs measurements and then the measurements of anomalous gauge, or the gauge triple and quadruple gauge couplings. That interplay should start to get interesting, I think, in run 2. But maybe one message I wanted to give here is that LHC Chapter 2 is sort of in a transition phase. So if we sort of carry this metaphor of a book a little further, then I think what we had up to now is sort of was a thriller where the plot was rapidly changing and there was lots of exciting new things happening on a short time scale. And now it's settling into more of a deeper book. You actually have to read through a lot of pages before something new happens. And in fact, I think in many cases we actually know how the story is going to turn out, unfortunately, because because of this, maybe the curse of the 95% exclusion versus 5 sigma discovery. So this, of course, assumes that you don't improve your analysis technique, which you're always trying to do. But if you don't improve the analysis technique, then as you saw in some of the prospect plots before, which were comparing 300 inverse femtobarns to 3,000 inverse femtobarns, so a factor of 10 improvement in integrated luminosity, you can see sort of the difference, actually the almost negligible difference between 95% exclusion and 5 sigma discovery. And so what this means is that if at the end of run 2, with maybe 4 times more integrated luminosity compared to the results that have already been shown, the exclusion results, it's going to be, without any improvements in analysis technique, it's going to be very hard to have a 5 sigma discovery in those channels. So we already know how the story is going to turn out in some sense. It's kind of depressing. Yeah. Let's look at, this one will do. So in the black is the 5 sigma discovery at 3,000 inverse femtobarns, right? And then this one, the red one, is the exclusion at 300 inverse femtobarns, factor of 10 less luminosity. So if I already excluded at 300 inverse femtobarns, there's no chance of getting a 5 sigma discovery with 10 times more data. It's excluded. All of this is excluded. So there's no chance of 5 sigma discovery. And this is a factor of 10 in integrated luminosity. So in run 2, now what we're talking about maybe a factor of 4 more by the end of run 2. So, but again, this is, prove the analysis. If you're running the same analysis and you optimize, very unlikely, I think, that for many of these, well, okay, we don't improve anything, which is not the case. Like I said, we're always trying to improve. It makes it very difficult to discover something just by increasing the luminosity. So of course, there are some excesses now. Maybe not that big, but those could turn into 5 sigma effects. Also, it's possible that even if one doesn't see anything, so one can't claim 5 sigma with 4 times more integrated luminosity, maybe one starts to see a 2 sigma effect. So it could be more exciting than I've said here. So really given that the luminosity doubling time is getting much longer now, one can think of it as an opportunity or maybe even a need over the next years to really rethink deeply the strategies that we're taking. So one question that's always asked is, have we covered everything? So this comes up all the time, and it's a worry. I think it's maybe not really possible to answer completely, to cover every single loophole. That's probably not possible. As you probably know, there have been some attempts, at least in the SUSY group, to try to approach this question a little bit more systematically. So trying, for instance, the scan and the PMSSM, which which is a fairly general scan, and seeing where the current searches are falling short. It's possible that Atlas will undertake some of these in the future, maybe more concentrated scans in a smaller subspace. So looking, for instance, maybe a 4-parameter scan for electroweak SUSY, or a slightly larger scan in 3rd generation. Rather than doing this 19-parameter scan over the full PMSSM. So then I think in addition to trying to think about, unknown signatures that we haven't thought about yet, I think it would be useful to think more about how to improve the already known signatures. And this is going to be quite difficult to improve these analyses, and so it's nice to have maybe some indication of which ones have the biggest potential and where we should be focusing our work. So clearly, there's close collaboration with the phenomenology community is essential here. And so then that leads to the last, which is I guess I have about 5 minutes, the presentation of results for interpretation outside Atlas. So I don't know, I think a lot of this might have already been covered in the last week. There's already been working groups meeting on this. So I maybe go through this rather quickly. But so as you probably know, there's an internal set of guidelines in Atlas for how to present results from at least from SUSY and exotics groups, which try to be in line with these Les Houches recommendations from a number of years ago. And in general, people try to make an effort to apply these uniformly across all the analyses. I think maybe in SUSY it's a little bit more successful, probably mainly because the search target and the analysis techniques are more uniform across the groups. It's maybe less uniform in the exotics. So I'll just give a few examples in the coming slides. So this is the output of a typical SUSY analysis, which is in Atlas at least is a set of single bin cut and count signal regions. And so for each signal region, what we call the model independent limit is provided. So this is, although it's written in a somewhat complicated way, it's just the minimum number of signal events that are excluded at 95% confidence level divided by the integrated luminosity. Okay, and so then it's written as this sigma visible, which is the acceptance times the cross-section times the efficiency. And this is an example table from one analysis, the stop search, that shows the numbers for this visible model-independent visible cross-section. So if one were to try to use this number on a new model, then you need to know the acceptance and the efficiency of this signal region for your new model. And so to help with that calculation, there's a set of numbers that are put into HEPdata. And so this is an example. This is the interface to HEPdata, which you can usually follow. You can find the link if you grab the paper from Inspire, for instance. And so this is a table showing the acceptance for in the stop search in the stop neutralino plane. These filters are definitely handy too, because there's a lot of material that's put into HEPdata. Using the filters is quite handy. Also, this the resource link is also quite useful. So this is what the acceptance and the efficiency looks like. So the acceptance is calculated with objects at truth level, and there's a description of what's actually done. And then all the experimental effects are absorbed into the efficiency, which is computed after applying the acceptance cuts. So the product gives you the full selection effects. So this is just a few examples of the acceptance and efficiency for from some of the signal regions in the stop analysis. Something new from 2017 are these snippets of code. It's sort of pseudocode that gives the cut flow for the acceptance selection. So that can also be used in order to match up with the tables in HEPdata. So less ambiguity. Then other information that's stored are the contour lines. I'm not sure how useful that is in numerical format. And then also upper limits on the cross-section for a particular model. So they're corrected for the acceptance and efficiency for that model. And then also for some models, there's a detailed cut table for cross-checks, and then also the SLHA files. And so there's a workflow here that one could follow. I don't think I'll go through it now for how this can be used for recasting. Maybe just to add a few remarks. So this is what was described very quickly, but so far was the sort of the minimal set, which should be available for all the SUSY analyses. But in some cases, you need some customized information. So for instance, long-lived particle searches. And so here, there's an example of additional information that's provided. So there's a parameterized selection efficiency as a function of lifetime, which could be applied to at truth level to some other model with long-lived particles. So then, but it's clear that the analyses are becoming more complex, so there are more fits to multi-bin distributions. So that's being discussed already with the simplified likelihoods as one approach. Also the use of BDTs and other or machine learning techniques. And so there it's under study, at least inside Atlas, on how to tackle these issues. And probably the minimal solution is to provide, sort of like CMS is doing, these aggregated signal regions. So if one goes to multi-bin distributions, one would also provide the old-fashioned single-bin cut and count regions. Also, I think the analyses are becoming more varied, and so a common approach becomes more challenging. I think this is also something we need to think about in the next years. In some sense, the exotics group, partly one reason why maybe they're less uniform in the material that's provided is that there's a larger variety of analyses going on. And so here are a couple of examples of what's done in the exotics groups. So you could try to produce conservative particle level estimates in the case where the efficiency is only slowly varying. So you could find a minimum efficiency and call that the conservative estimate, and then that one provides sigma.a. So the only thing that if you're recasting you would need to do is calculate the acceptance of your model. So one example of that is this monophoton analysis from the exotics group. The other, I think you've already heard about, maybe from Darren's talk or in some of the discussions, are the differential distributions that are folded to particle level. So an interesting one was this case of the ratio of cross-sections defined in a fiducial phase space, and then several differential distributions are published. And so, these unfolded distributions are made available, including all the bin-by-bin correlations and a rivet routine. So this, in fact, is standard for all what Atlas would call measurement papers, and in some sense it blurs the distinction now between measurements and searches. And so another example is this 7 TeV double differential dijet cross-section measurement, which was unfolded to particle level. And these are the limits. This is a limit on contact interactions that come from the unfolded distribution. And they turn out to be similar limits to those obtained from a search for contact interactions at RICO level. Now, whether this holds for all analyses is probably doubtful. This is actually an area of investigation in Atlas. But this is at least encouraging and interesting that they have the same sensitivities to new physics. I think I'm going to skip this. There are other approaches for resonances, but well, we can look at them later if we like. I want to finish with one example from the Higgs group, which took me a little bit by surprise, actually, even though I'm in Atlas. Because you often hear that Atlas would never provide likelihood distributions to the outside world, but that's not the case. That's not. So there's one case here for the Higgs discovery paper where Atlas uploaded the likelihood function as a function of the signal strength in 2 dimensions. And in fact, this HEPdata has 8 citations. And one of them, it's interesting, from this paper in the appendix, says after the original, so this is a sort of a type paper for recommendations for Higgs analyses, what type of information to provide. And so there's an interesting observation that in September 2013, after the original submission of this note, the Atlas collaboration digitally published the likelihood in a grid on this mu plane associated to these decay modes. And so with that, I'm going to go to the last slide. So yeah, Atlas does listen to the theory community, maybe only sometimes. So I'm definitely looking forward to the discussions at the workshop. Okay, thank you.